Hey guys, Mr. Smith here, and in this video lesson, we're going to develop Young's double-slit equation. So to start, I actually got a visual here of a 2D interference pattern using some dripping faucets. So their distance between the drips is not changing. The frequency of drips is identical, and they're in phase. They're dripping at the same time. And so we've got this 2D, you can see these circular waves propagating out from each source, forming this interference pattern that we've talked about. So you can see as they ripple out, the circles of brightness, like the crest, the circles of darkness, the trough, and where those meet, we get these nodal lines of destructive interference. And so you notice they're dark, so that would be like calm water, let's say, in terms of a ripple tank, if this was water. Now, the issue is if we want to observe this kind of thing for light, the wavelength of light is so small, and these nodal lines are going to be like so kind of tiny that, and these path differences so small, there's no way that we could really measure them. So we have to figure out some way to take our 2D interference pattern here for like water waves and get a way to think about that in terms of light. So that's kind of the purpose of our what we're doing right now. So let's get started with our lesson. We're going to develop Young's double-slit equation. So in our initial analysis, the path differences depended on the nodal lines. And the relationship we found before for the path difference was this. You get a point in the nodal line, the distance from that to the first source, minus the distance from the same point to the second source. It was always a multiple of the wavelength, and that multiple was the nodal line minus a half times lambda. So we developed that in our previous lesson. We called this the path difference. Again, Pn was a point on the nodal line, S1 and S2 were our sources, and N was our nodal number, telling us which nodal line, 1, 2, etc. So if the problem kind of is, though, for us, if the wavelengths are small, or the point P on the nodal line is far away, the path difference will be very small. And it's going to be hard to calculate this. And so for light shining through two slits very close together, wavelengths of light are small compared to the size of two very small slits, like very close together, like less than, like we're talking fractions of a millimeter. Those points on the nodal lines that we'll be able to measure are like far away. And the path difference is going to be very small, very hard to measure. So we're going to use another technique to analyze path difference. So let's get started. So consider this setup here. So this is kind of the setup we had before. So we have two sources, S1 and S2, and they're separated. Their slit separation, their source separation is D. And we have some nodal point, Pn. And we've just got some point A. And this A is special. A comes from when we take our just nodal point diagram and we have our path difference diagram, and we create an isosceles triangle. And by doing that, the path difference actually becomes visible. The path difference is the distance from A to S1. So A is that point that represents the path difference. Because you can see from S2 to Pn and from A to Pn is the same. That means from A to S1, that has to be the path difference. So AS1 is our path difference. And what I want you guys to envision taking that point far, far away. Just drag it really far away. And this would be what it's like for us, because if we're doing shining light through two very narrow slits, the D is extremely small. And so PN, compared to that, PN is going to be very far away compared to that small distance. So taking PN far away here makes a lot of sense, because this D distance is super small for light. And what you get is you get those two lines that like those the APN and S2PN, those two sides of that isosceles triangle, they get basically parallel. Because you can think about that. As you drag the PN far away, you still have an isosceles triangle. But, you know, you get if like you have an isosceles triangle and the top angle is 2 degrees, then the angle at the bottom, you get 89 degrees and 89 degrees, right? Just, I guess you can't really see that. 89 degrees, 89 degrees. And if you just go farther and farther away, that angle up top gets smaller and smaller, and those two other guys get close to 90. And like two 90-degree angles, 90 degrees, they're going to be parallel lines, right? So this angle at A approaches 90 degrees because those two lines would be parallel. And I will just add here, the lines are approximately parallel. So pretty much parallel, but it is approximate. So the new expression we get for path difference is going to be approximate. It's approximately parallel. All right. And we call this angle down here theta n. Now, what you guys are going to see in a second there is that if our point PN is far away, the angle from the center line up to that angle is actually theta n2. And that angle is actually going to represent the angle our nodal lines are at. If you remember, we talked about how the nodal lines are approximately straight. Well, if PN is really far away and the slit separation is small, then they pretty much are straight. And we're going to develop a formula that predicts the angles that the nodal lines are at. And we can use this triangle down here for that. So yes, I do have space for that over here. All right, so let's continue. So from our diagram, we had that before, doing SOHCAHTOA, the sine of that theta n is equal to the opposite AS1 over hypotenuse D. Just commit yourself there. D is the hypotenuse in that triangle. And that path difference, AS1, again, that's our path difference, is the opposite side. So the sine of theta n is AS1 divided by D. And so D sine theta, or D sine theta n, equals AS1. But that's the path difference. But we actually did a lot of hard work already to get an expression for the path difference, right? The expression for the path difference was PNS1 minus PNS2. And finally, PNS1 minus PNS2, we said that was n minus a half times lambda. So this is really cool, guys. If I rearrange that, this can go in the box here. We get an expression for sine theta n equals n minus a half times lambda over D. So guys, if you know your slit separation D, and you know the wavelength of light that you're shining through, and I'll say this now and I'll mention it a few more times during this lesson, but in these experiments with light through double slits trying to show these 2D interference patterns, it's important to use lasers, because a laser is just a very focused one wavelength of light just coming out at a very high intensity. So a laser just narrows, it's not like white light that has all the different frequencies of the spectrum. A laser is giving you one or a really small range of frequencies. So if you're using a laser, you know lambda, and you know this the slit separation, you can actually predict the angles of the nodal lines. I think that's really I think this is really cool. So this formula predicts the locations of the nodal lines. And you know what? I think since we have space here, so we know the nodal lines kind of come off like that, right? So this equation gives you, this equation helps you predict those. So for example, if you want to know the angle, excuse me, that's the wrong one. If you wanted to know the angle of like the third nodal line, then you just plug n equals 3 into that formula and then solve for, and then just do inverse sine. So I think that's like very, very fascinating. Yeah, so the third nodal line would be like this. That'd be theta 3, for example. All right, and this equation we have here, I might just highlight it too. You know what, actually, I meant to highlight the one above that. So let's fix that up. This equation here is another way to find the path difference. So we have one way already. Remember, the one way was knowing n and knowing lambda, you can get the path difference. But this says the path difference is also equal to d sine theta n. So this is an approximate path difference formula. So it's a new approximate path difference. So it's in saying instead of taking a point on the nodal line, you just measure the angle of your nodal line, and using the slit separation d, you can calculate the path difference too for any point on that line. So that's pretty neat. So just in our development, a couple of new equations. We have an equation that tells you how to get the path difference in terms of the angles for the nodal lines. And we have an equation that's really cool. Given the wavelength of light you're shining through your slits and the slit separation, you can predict the pattern of these nodal lines, where they're going to appear. So pretty neat. All right, let's keep moving. So in a wave tank, like we have here, you know, this is like, imagine this big enough water tank. Like I could physically measure these angles that these nodal lines are at. But you know, if again, because we're the D, our slit separation, if we're shining light through two narrow slits, it's going to be a lot harder to calculate. Wavelengths that are tiny, like light, and slit separations that are small, the angle is going to be small because all the nodal lines are close together, and so yeah, it's still not really practical for us to measure these nodal lines for light. For water waves, all this is great, but we need something more for light. So this is what we're going to do. So remember, guys, we imagined our PN being very far away. So this diagram is definitely not to scale. So S1 and S2 are our two slits, and they're separated by our distance D, which I think I can add on there. We're going to add various things to this diagram. Yeah, I'm going to call this the center line C, and our plate separation, we're still calling D, the distance between the two sources or our two slits. And remember, for light, these two, the D is super small, and PN is very far away. We're imagining taking PN to a screen very far away. So we're shining light through two slits, and we're thinking, what will I see on a screen far away? Remember, guys, those nodal lines are destructive interference. They're going to be dark. So we're kind of predicting, where are we going to see dark fringes on a screen far away? So this diagram is not really to scale. D is so small, PN is so far away. And if you recall, we said that these two sides will be approximately parallel. Like, obviously it doesn't look like that right now because, you know, I want to actually draw a diagram with you guys. But in reality, D is so small, but we make do with what we have. So I'm going to add a couple things on there. We are going to call this horizontal distance from the center line to some nodal point on the nodal line N. I'm going to call that xn. And I'm going to draw, oh, I wish I had used, you know what, guys? I'm going to just draw, because I want to make sure this line is super straight. I'm going to draw a line in right now. That's how important I consider this line. Okay, good enough. Let's continue. So this purple line I drew here, remember that represents the nodal line. So this would be that dark line, or in a ripple tank, that line of calm water. And I'm going to add a little label to that. Have to find my cursor. Oh, we are having a time today. Where's the cursor? There it is. All right. This guy is our nodal line. That's bugging me there. All right. After like a minute of fooling around here. This is a nodal line. So just our familiar good old nodal line for a certain nodal number. We're gonna say this nodal line has a length of L. Okay. And a couple other things. So we've got C, we've got D. I'm going to throw in, if you recall, we had this right angle triangle here formed by point A, and we called this the path difference, right? This was our path difference, AS1. And this was our theta n. Now, maybe last lesson, you were like, I don't get how theta n gives you, in that diagram we had, not lesson, like the last slide, I don't get how theta n gives you the angle for the nodal line. How are those connected? Well, I'll show you. And it has to do with similar triangles. So the angle at A is a right angle triangle. The angle at up here is obviously a right angle. We have a screen. We have a vertical line. And if you look at the line joining the sources, the screen, those are parallel, right? If you look at the line joining S1 and PN, this angle is the same. This guy here that I just marked up is the same in both of them, which means, and you guys learned this in your grade 10 math course, with similar triangles, like if two angles are the same, you have two similar triangles, they have the same shape, which means the third angle is the same, which means this angle tucked in right here is actually theta n as well. So it gives you the angle of the nodal lines. So that's pretty cool. So from here, I just have various things to add in the white space to the side, and we're just going to develop some equations. So first, let's label what xn is there. Xn is the distance from the right bisector. Or you know what? Let's just say the distance from the center line. I think it's clear what the center line is. All right, so xn, distance from the center line. L is the length of the nodal line. Corresponding to Pn. Maybe I'll add that, C to Pn. All right, and theta n is the angle of the nodal line from the center line. So I think all that stuff's kind of clear from like what we were chatting about and labeling on the diagram, but we just got those down there. All right, and as we've talked about, for I think I have it in here, for small d and small wavelengths, like light shining through double slit, these nodal lines are basically straight. So these angles are giving us these straight lines. And that brings us to our next step in our development. We use some trigonometry. Again, the sine of theta n. And this time, instead of looking at the triangle A, S1, S2, we're looking at the triangle formed by C and then the 2 points on the screen far away. The sine of theta n is opposite xn, so that distance from the center line horizontally, divided by the hypotenuse, L. And if we plug in what we know from earlier, remember, guys, sine theta n, we actually got an expression for that. Given the wavelength in d, it was n minus a half times lambda over d. So let's plug that in. N minus a half times lambda over d equals xn over L. And from that, we're going to do a little bit of an analysis. So I'm going to go over on the front here. So to summarize, let's just summarize all we know, because we've done a lot of things, we've drawn a lot of diagrams. So the very first thing we did was, given a nodal point, we can make some measurements. And the path difference, like literally just measuring it on a diagram, was, we know that's n minus a half times lambda. But we also showed that d sine theta n was equal to n minus a half times lambda. And then finally, we just showed this as well. Something else is equal to n minus a half over lambda. If you multiply up the d, look, you have n minus a half times lambda by itself. So one last expression we just kind of developed, xn times d divided by L also equals n minus a half times lambda. So all three different ways to find the path difference. You could actually just measure the path difference. You can get the path difference if you know the slit separation and the angle of your nodal lines. Or you could get the path difference if you knew the slit separation, you knew the length of your nodal line, and you knew the horizontal distance from the center. You could find the path difference. And lastly, in this box down here, I guess I've got a lot of space for this, but the last thing I want to put in this box is a way to predict that horizontal distance. If I solve that last equation for xn, I get the following. Xn equals n minus a half times lambda L over d. And why is this important? This is almost like the big finale equation. I just came up with that on the spot. But I encourage you that our development is pretty much done. This formula, if you know basically your slit separation, the light you're shining through your slits, and essentially how far away your screen is, then you can predict where the nodal lines will be. You can predict where the first one is. You plug in 1, you plug in 2. So you can actually predict on a screen far away. You can predict, here's my first one. Here, you can predict where the darkness is going to be. And that's really good, because if you can make predictions, we can do this experiment on a screen far away from double split and actually see if where the predicted dark spots are going to be, we can actually see if they're there. That's pretty cool. All right, guys. This brings us to Young's double slit equation. So let's add a few things on here. Here's what we think we'd see. So if we've shone light through some double slit, again, where the nodal lines are, that's going to correspond to dark fringes. So I think I'll have to use yellow, because I want to add something on over top of this. Yeah. So the distance, this distance here from the center line to that first dark fringe would be x1 with our previous equation. And then the distance to the second fringe would be x2, and so on and so forth. But something that's maybe a bit easier to measure is actually just the difference between, like the distance between the dark fringes. And so the difference between them, we're going to call delta x. So I'm actually going to add some nodal lines to my diagram. Just going to call a bit of an audible here. And I would actually maybe encourage you to use a ruler. But I'm going to draw the nodal lines. I'm going to draw that nodal line there, and then I'll clone it, draw another nodal line there. I think I'll draw one more. Yeah, I'll draw one more, and that will get the idea. Draw the third nodal line there. There we go. And then we'll continue. All right, so there's our first, our second, our third nodal lines. X1 is the distance to the first one from center. X2 is the distance from the center to the second one, and so on and so forth. But something that's easier to measure is actually just the distance between the nodal lines. So right in here, I want you guys to label, we're going to call that delta x. Delta x. And in our diagram, delta x is the distance between fringes. And I'll say too, dark and light fringes. Because all the math we're doing right now predicts where the nodal lines will be, which is just by definition where the darkness will be. But the distance between the dark patches is going to be the same as the distance between the intense bright patches as well. All right, so we've established that. I want to just clarify one mathematical thing too. So if you recall earlier, we said that sine theta n is equal to xn over L. Now, when theta is really small, when theta is I'll just say is small. That's fine. I was thinking of a fancier word to say that, but that's fine. When theta is small, you can check this on your calculator. Sine theta and tan theta are approximately the same thing, because the hypotenuse and opposite side are the hypotenuse and the opposite side are so close together that I think the hypotenuse and the adjacent side are so long that O over H and O over A actually become very close. So when sine theta is small, we get sine theta equals xn over L, and so now we'll use the tan of theta n equals xn over L. And we can do this because, again, the slit separation is small. The angles are really small because the wavelength of light is small. But if the tan is xn over L, well, tan is opposite over adjacent, which means adjacent side is L. And this will be helpful for us because, the nodal line is hard to measure, but we can measure the distance from our double slit to the screen far away. It's just that vertical separation. So now, instead of L being the length of the nodal line, L is the distance to our screen far away. And if you're thinking, well, how can you just change L being one thing to another? They're not technically equal, but we've explained approximately why they're close. And this is a good approximation. So yeah, we can move forward from that. All right, so we have discussed at the dark fringes, we had the following. The distance, xn, was equal to n minus a half times lambda times L over D. Wavelength, distance to screen now. So L is how far away the screen is, easy to measure. D is the plate separation. How far apart are these? What is delta x? So to illustrate that, let's get an expression for x1. So x1 is, if you plug in 1, you get 1 minus a half times lambda L over D. And this is 1 minus a half is a half, so you get lambda L over 2D. And if you look at x2 would be 2 minus a half lambda L over D. And 2 minus a half is 3 halves, so you get 3 lambda L over 2D. And if you look at the difference between those two, x2 minus x1, you get 3 lambda L over 2D minus 1 lambda L over 2D. Well, those are common denominators. I could subtract them, and those are like terms on top. I get 2 lambda L over 2D, and I actually get lambda times L over D. It's pretty interesting. So guys, think about how fascinating this is. So we've done a lot of equation development, I know, but look at this result. It's so awesome. If you know the wavelength of light you're shining through 2 slits, you know how far away the screen is L, and you know the plate separation, the slit separation D, you can predict the distance between where you see the darkness and the brightness on a screen far away. So this is easy to, if you just create a little double slit and shine light through it. This is something easy to predict. This is an easy equation to use, and it's something easy to actually verify and measure as well, right? So this is the basically Young's double slit equation. We did it, guys. So just going to kind of summarize Young's double slit equation on this slide. You guys should have lots of room on your on the front side of this sheet, or where we had the last diagram. So if we rearrange things, we get this: delta X over L equals lambda over D. So the ratio of the wavelength to slit separation is the same ratio as the distance between your fringes and how far away the screen is. So this is awesome. This is Young's double slit equation. And let's reemphasize, L is the distance to screen. D is the slit separation. L is the wavelength. And delta X, the distance between fringes. All right, so maybe a couple things, and then before we wrap up this lesson. So Young's double slit equation gets you delta X. If you actually want to know where from the center line these dark bands would be, well, X1, you can still use your old equations, but like X1 would be half of delta X away from the center line, and X2 would be 1.5, and X3 would be 3.5. And you can just see from the diagram, right? Because over here, this would be another delta X, right? So it's from the center lines, so it's half delta X, then 1.5, and then 2.5. And again, if you want to see these fringes for a specific color, you've got to use lasers through these to make sure it's a very specific wavelength. If you shine white light through, you get a really cool visual, like in the Veritasium video, but it's harder to measure the distance between the dark fringes and light fringes, because there's a lot of light fringes of different colors and intensities. So, all right, Young's double slit equation. So given any of these three things, you can predict the fourth. But yeah, the big idea, guys, is that now we can make predictions. So if the light is a wave, and I shine light of a certain wavelength through a certain slit, double slit, to a screen, a distance I know how far away it is, I can say, well, if light's a wave and I do this, I should be able to see dark fringes here, 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 and here with this distance. And you can carry this out and actually like verify this. And it was done. They did it over and over, different slit separations, move the screen farther away, change the type of light you're shining through the double slits, and this held. And so it was undeniable proof that light actually does diffract. It follows these 2D interference patterns, and light is a wave. So did that mean, so there was people in both camps, light is a wave, but we also have evidence that light is a particle too. So did that mean that light's not a particle and those people were wrong? Well, that's what we're going to investigate in our next day of lessons, our final day of lessons, when we look at quantum mechanics and look at the particle theory of light and start to make connections between all matter and waves. So it's going to be pretty interesting. So that's it for light as a wave. I wish we could do a lot more with light. If you watched both crash course videos, you would have seen some more interesting things on thin film interference, like why kind of bubbles look the way they do, and like soapy, filmy kind of stuff. Yeah, there's a lot more we could have done, but just time just doesn't allow it. So check out the 2 crash course videos. Definitely informative. You can learn a few more things. But for us, the undeniable proof that light is a wave came from looking at Young's double slit experiment. So I hope you enjoyed that. Good job with all the equation development. I know it was a little math heavy, but the payoff was really cool. All right, guys, I'm going to sign off. Hope you're staying well. Have a great day, and we'll see you soon.